Welcome back to my channel. Today we're going to be talking about Riemann sums with summation notation and definite integrals. So Riemann sums are the area of rectangles added together. When we talk about repeated addition in math with this specifically, we're going to be talking about what's called a summation. So a summation uses our uppercase sigma. We need a variable and a starting place. This is called the index. So a lot of times they go with k equals 1. Sometimes they go with I equals. And then we need a stopping point, which is going to be on the top, which we're going to use n. So once we get to that number, that's when we stop adding the next term. And then we generally have some sort of equation here, and it's going to be in terms of our variable of the index. So in terms of k. So when we talk about summation notation, what we're looking at is something like this, where we can take that value k and we say, oh, k is 1. Now we're going to add it to when k is 2, when k is 3, when k is 4, and then finally when k is 5. So we're going to plug that value for k in, and then we're going to add it to when we plug in the next value and the next value. And that's what a summation does, which is why we talk about it as repeated addition. So what would our Riemann sum look like in summation notation? So we're going to use I for this instead of k, but we could also use k if we really wanted to. So we have our sigma, which is our automatic sign that it is a summation. We're going to do I equals 1 to n, because we don't know how many rectangles. N is the number of rectangles. So this right here is that number of rectangles. And then what we need to do is make our equation. So one of the things that we're going to look at is what we think of when we're doing Riemann sums. So when we're doing Riemann sums, we're going to have a base and a height. Our base is always the change in our x values. But we also need to multiply this by our index number, because that change is going to increase over time at what change in x we're talking about. So this right here is the base. The base. And we need the height still. Our height is found by y values. So we're going to take whatever our function is, f of So one of the things that we want to be careful of is, as I'm looking at this, ci, we don't actually want it to be ci. We want it to be x sub I or c sub I. The reason why is because we want to know which value we're talking about. Then we're going to look at this in a slightly different way. For what we want to do with our sigma notation, this is going to look something more like the following. So our k equals 1 to n for our sigma notation. We are still going to have delta x. This is just the difference in our x values. And then we're going to have f of a plus k times delta x. A is our starting value. It's where our function is going to be, or x value that we're starting at. And then our interval times our change in x gives us the next x value. So we're looking at how do we make a system to kind of help us decide what our function is and how it changes over time. Okay. So when we look at here, for Riemann sums, the number of rectangles is n. In order to find the area of the rectangle, we need to take the change in our x value and multiply it by the height of our x value. This is going to look like delta x times f of x. In order to get our total area, we're going to add all of those things together. So we are going to do the summation from whatever variable we're dealing with, 1 to n, of delta x f of x. When we are talking about the exact area, the number of rectangles that we're looking at are going to be an infinite number of rectangles. The rectangles that we're looking at are still f of x in height, but this time our d of x is that change of x. So we have f of x times d of x, or d of x times f of x. F of x times d of x just feels better. So when we do our summation, we're going to talk about the summation from our starting point to infinity of f of x dx. So what we're going to do is we are going to take those things and kind of help us out by adding them to a limit. So if we increase the number of rectangles towards infinity with a limit, we have the limit as n, because it's the number of rectangles, goes towards infinity, of our summation from k equals 1 to n, and we're going to use our f of a, 1, so our function where we have a starting x value, or starting x value a, plus our change in x times our index. And we're going to multiply that by delta x. This right here is the limit version of the integral from a to b of f of x dx. So one thing that we need to know is, what does delta x refer to on our interval of rectangles? So when we're talking about delta x, that change in x, we're going to be looking at the distance between our endpoints, so b minus a, and divided by the number of rectangles we want, so b minus a over n. This is all going to be what helps us change these sigma notation and integrals.